You know all those data structures and algorithms you learn about in school? Well, we're going to go way beyond the textbook today. We're diving into the wild to see how the absolute titans of the internet, systems like Linux and Redis, use these exact same tools to handle insane amounts of traffic. This is where theory meets reality. Let's get into it.
So let's just start with the big question, right? How on earth do systems like Linux and Redis handle millions, literally millions of requests without even breaking a sweat? I mean, we're talking about the core of your operating system, the backbone of countless apps. How do they stay so fast and so reliable? It almost feels impossible. But here's the thing. It's not magic. Not at all. It's just really, really good computer science. See, this kind of performance doesn't happen by accident. It's a series of deliberate, incredibly smart engineering choices. And it all boils down to one thing: picking the absolute perfect tool for the job. And that's exactly what we're going to do. We're going to open up the high-performance toolkit. We're going to meet 4 data structures that are pretty much the unsung heroes of the modern internet. Seriously, these are the fundamental building blocks of speed and reliability. So let's meet our cast of characters. Okay, first up, the red-black tree. Now, this is a type of self-balancing binary search tree. But forget the jargon for a second. Just think of that analogy: a perfectly organized bookshelf that automatically rebalances itself every time you add or remove a book. That's the superpower here. It means that whether you have 10 books or 10 million, finding any one book is always super, super fast. That's what we mean by O log n performance. And the keyword here is guaranteed. That guarantee is why systems that absolutely cannot fail love this thing. Next on our list is the X-array, which is basically a souped-up version of a radix tree. And here's the mind-bending part. Its speed has nothing to do with how many items are in it. 0. Instead, it's all about the length of the key you're looking for. The address analogy is perfect. To find my house, you go to the country, then the state, then the city. It's a set number of steps. It doesn't matter if there are a billion other houses in the world. Those steps don't change. It's a really different way of thinking about performance. All right, now for a true classic, the hash table. Everybody knows this one, right? It's the poster child for pure, unadulterated speed. The dream is what we call O of 1, or constant time access. That means it should take the exact same amount of time to find an item, whether you have 10 items or 10 million. You just go right to it. The labeled bins analogy nails it. If you spread everything out perfectly, lookup is instant. But notice that big if. We're definitely going to circle back to that little word. And our final tool is the skip list. Now, this one is really cool and maybe a little less famous. It's what we call a probabilistic data structure. I love the highway analogy. Imagine a regular linked list is just a single slow lane. A skip list adds these express lanes on top. You jump into the fastest lane you can, cruise along until you're about to pass your exit, then drop down to a slower lane and repeat. It's not a guarantee like the red-black tree, but it gives you that same O of log n speed on average, and this is a big deal. The code is often way, way simpler to write. Okay, so we've met our 4 contenders. We know what they are in theory. But now for the fun part. Let's see how these things actually work in the wild. We're going to see how these abstract ideas are used to solve incredibly high-stakes problems in systems you probably use every single day without even realizing it. So let's start at the very core of your computer, the Linux scheduler. Think about its job for a second. It's like an air traffic controller for your CPU. It has to juggle dozens, maybe hundreds of processes, give every single one a fair turn, and make the decision of who goes next millions of times a second. How in the world do you design something that's both fair and lightning fast? Well, the answer is it uses a red-black tree. The Linux Completely Fair Scheduler, or CFS, is built around it. Here's how it works. Every task is placed in the tree, sorted by something called virtual runtime, basically how much CPU time it's had. Adding a new task is fast, that O of log n we talked about. But here's the absolute genius move. To be fair, the scheduler needs to pick the task that has run the least. In a sorted binary tree, where is that task? It's always the one all the way to the left. Finding that is an O of 1 operation. It's basically free. It is the absolute perfect tool for this exact job. So elegant. Okay, let's switch gears to Redis. You know, the ridiculously fast in-memory database. Redis has this really powerful data type called a sorted set, or a Z-set, and it presents a really tricky problem. You need 2 things at once. You need to find any member by its name, like instantly. But you also need to find members based on their score, like give me the top 10. These 2 operations are usually at odds with each other. So how do you get the best of both worlds? The answer is just so clever. Redis doesn't pick one, it uses both. It's a hybrid solution. On one hand, you have a hash table. This gives you that insane O1 lookup speed to find any member by its key. At the exact same time, it uses a skip list to keep all the members sorted by their score. This gives you the fast O-log-N performance for all your ranking and range queries. It's not about picking one tool, it's about combining them to create something even better. Just brilliant. And they don't stop there with the clever tricks. You know how I mentioned that if with hash tables? Well, one big problem is when they get too full, you have to resize them, which can cause a big laggy pause. Redis knows this, so instead of a stop-the-world pause, it does something called incremental rehashing. It just moves a few items over to the new, bigger table every time an operation happens. It spreads the work out over time, so no single client ever feels that painful lag. Again, it's all about making performance smooth and predictable. So we've seen a couple of amazing examples of how these things are used. But now let's get to the really important part, the why. Because being a great engineer isn't just about memorizing the big O complexity from a textbook. It's about something much deeper. It's about truly understanding the trade-offs. And this table really puts it all in perspective. You look at the red-black tree and you see that beautiful O of log n in both the average and the worst case. That's a guarantee. That's why the Linux kernel, something that absolutely cannot have a bad day, relies on it. Then you see the hash table, O of 1 on average, which is incredible, but a potential O of n nightmare in the worst case. And then the skip list. Its average case is great, O of log n, but its worst case is technically O of n, just like the hash table. So that begs the question, why would a system obsessed with speed like Redis ever choose that over the guaranteed performance of a red-black tree? And this gets us to a huge myth that a lot of us learn early on. We're told hash tables are O of 1 and we just accept it. But here's the reality. That's the expected performance. That's the best case scenario. In the real world, if your hash function isn't great or you don't resize it properly, the performance can absolutely fall off a cliff all the way down to O of n. The real world is always messier and more interesting than the textbook. So why are we going so deep on this? What's the big takeaway for you? Well, it's simple. Understanding this stuff, the real-world applications, the messy trade-offs, this is your engineering edge. This is what separates you from the pack in a job interview and, more importantly, in your actual work. So let's boil it all down. Here are the key things to remember. First, performance is so much more than just big O. It's about predictability. A slightly slower but consistent system is often way better than a sometimes fast, sometimes slow one. Second, real systems get creative. They mix and match data structures, like Redis did, to solve complex problems. And third, and this is a big one, simplicity can be a feature. The reason Redis chose a skip list, part of it was because it's way less code and easier to get right than a red-black tree. And in the real world, that matters a lot. That kind of thinking is what great engineering is all about.
And that really brings us to the core idea I want to leave you with. Look, anyone can cram for an exam and memorize the big O of a dozen data structures. But a truly great engineer, they've mastered the trade-offs. They know not just what the tool is, but why you'd choose it, and just as importantly, when you wouldn't. It's the difference between knowing the names of the tools and truly mastering the craft.